In this video, I will talk about Millman's theorem. If you follow this whole video, I expect that you will get a clear idea about Millman's theorem. Millman's theorem is a combination of Thevenin's and Norton's theorem. Thevenin theorem states that any linear circuit can be reduced to a single voltage source in series with a resistor, and Norton theorem states that any linear circuit can be reduced to a current source in parallel with a resistance. When I will be talking about Millman's theorem, you will see I will reduce all the parallel branches into a single voltage source with a single resistance or a current source with a parallel resistance. So Millman theorem is used to reduce any number of parallel voltage or current sources to an equivalent circuit containing only one source. That means after applying the Millman theorem, the circuit we will get will contain a single source. That means it could be a voltage source or current source, and it has the advantage of being easier to apply to some networks than mesh analysis, nodal analysis, or superposition theorem. Before applying Millman's theorem in any circuit, you have to ensure these three conditions. These three are the necessary conditions for applying Millman's theorem in any circuit. That first one is that the branches must be connected in parallel. Whether the circuit contains voltage source or current sources, they should be connected in parallel and cannot have more than one source in a branch. In the circuit, one branch will contain one voltage or current source. If we have more than one source in a branch, we will reduce that branch source into a single one. I will show you an example with that. And each branch cannot have more than one resistor. Okay, whatever the number of resistors in a branch, we will reduce that resistor into a single one. So after ensuring these three conditions, now I will go for Millman's theorem. We can state Millman's theorem in terms of voltage or current source or both. That means the circuit will contain both voltage source and current source. We can state Millman's theorem for three conditions: parallel voltage sources, parallel current sources, or parallel voltage and current sources. So at first I will talk about parallel voltage sources. This is the statement: if voltage sources V1, V2 for nth source Vn having internal or series resistance R1, R2 for nth resistor Rn respectively, and they are connected in parallel, then these voltage sources may be replaced by a single voltage source of VEQ having a series resistance of REQ, where VEQ is this and REQ is this. I will show you the detailed derivation of this VEQ and this REQ in this lecture. See, Millman's theorem states that if I have a voltage source V1 in series with R1, if I have a voltage source in series with a resistor R2, for Vn, if I have a series resistor Rn, I can replace this total network with a single voltage source VEQ in series with REQ with respect to this A and B terminal, and you will see the branches are connected in parallel and each branch contains only a source and a resistor, and we will calculate VEQ by using this formula: V1 divided by R1, V1 divided by R1 plus V2 divided by R2, V2 divided by R2 for nth resistor plus Vn divided by Rn, and here I will take 1 by R1 plus 1 by R2 for nth resistor 1 by Rn. This is how we will calculate VEQ, and we will calculate REQ by using this formula: 1 divided by 1 by R1 plus 1 by R2 plus up to 1 by Rn for nth resistor. Now I will show you the detailed derivation of these two formulas, VEQ equal to this and REQ equal to this. Okay, now let me prove the Millman's theorem. Millman theorem states that if I have a voltage source V1 in series with resistance R1, the voltage source V2 in series with resistance R2, just like this, voltage source Vn in series with resistance Rn, and all the combinations of voltage and series resistances are connected in parallel. See, they are connected in parallel. Then we can reduce this entire network to a single voltage source V equivalent series with a resistance R equivalent with respect to the A and B terminal. That means with respect to this terminal and this terminal, I can reduce this entire network to V equivalent and R equivalent connected in series, where V equivalent will be equal to this and R equivalent will be this. I will derive these two equations from our circuit. So at first you have to understand what is the VEQ. VEQ is the open circuit voltage drop across this terminal and this terminal. In some book you will see this voltage is expressed as VTH, because this voltage will indicate the same voltage we used to calculate the Thevenin voltage across two open terminals. Okay, here I will express this voltage as V equivalent. To calculate V equivalent, at first I will replace each of the voltage source and their series combination with a current source and a parallel resistance of same value using source transformation technique. See, with respect to these two terminal, I have a voltage source of V1 in series with resistance of R1. Therefore, I can convert this voltage source into a current source by using source transformation technique like this. I1 will be equal to V1 divided by R1. For V2 R2, I will get a current source V2 divided by R2. For nth resistor, I will get our current IN equal to Vn divided by Rn. And see, the direction of I1, I2 and IN will be in upward direction, because the V1, V2 or Vn will supply the current in this direction or in upward direction. Therefore our circuit will look like this. I will use the source transformation technique. That means the combination of voltage source with series resistance will be replaced by a current source with parallel resistance. See, I1 will be in parallel with R1, I2 will be parallel with R2. Just like this, IN will be in parallel with Rn, and all of them are connected in parallel. Now I will calculate the effective current through this AB path, just like we calculate the Norton current in any circuit. At first I will short this A and B terminal. After that I will calculate I equivalent. Now see, as this is our A terminal and they are all connected in parallel, this will be also A terminal, A terminal, A terminal, A terminal. This will indicate A terminal, A terminal. That means this line indicates the same node. Therefore, if I apply KCL at node 1, I will get this is incoming, and this is also incoming. That means the sum of current source will indicate the incoming currents. I can write only outgoing current is I equivalent, and sum of incoming currents I1 plus I2 plus IN. Okay, now I will calculate the equivalent resistance with respect to this terminal and this terminal, and I will express that with R equivalent. To calculate R equivalent in this circuit, if we have any voltage source, we will replace that with short circuit, and if we have any current source, we will replace that with open circuit. See, we have current sources here, so I will replace them with open circuit. After replacing the current sources with open circuit, our circuit will look like this. Now with respect to the A and B terminal, you will see all the resistances are connected in parallel. Therefore, if I want to calculate that resistance with respect to this terminal and this terminal, I will use the formula of parallel resistance. So our 1 by R equivalent resistance will be equal to 1 by R1 plus 1 by R2. Just like this, we can write it like 1 by Rn. Now if I take the reciprocal of this equation, I will get our R equivalent. From here I can write our R equivalent will be equal to 1 by R1 plus 1 by R2. Just like this, 1 by Rn. This is the second formula I have shown you while showing the Millman's theorem. Okay, so I have already deduced the second formula. Now if you look at the circuit connected between the A and B terminal, the circuit will contain current sources and resistances in parallel. According to Norton theorem, we can replace this entire circuit with a single current source. In parallel with a resistance with respect to these two terminals. And the current source will be equal to the current after connecting this A and B terminal with a short path, which I have shown you as I equivalent, and the resistance will be with respect to these two terminal after replacing the current sources with open circuit, which I have calculated as R equivalent. That means I can replace this entire network with a single current source. That current source will have a value of I equivalent, and that will be in parallel with R equivalent with respect to A and B terminals. After replacing the entire network with a current source of I equivalent and a parallel resistance R equivalent with respect to A and B terminal, just like Norton circuit, I will perform another source transformation. I will convert this current source to a voltage source in series with the resistance of same value. Let's say I denote that voltage with V equivalent. So if I perform source transformation, you'll see V equivalent will be equal to I equivalent into R equivalent, and this VQ will be in series with R equivalent. I have just performed a source transformation. I have shown you that I equivalent will be equal to sum of currents I1 plus I2 just like this up to IN into 1 by R1 plus 1 by R2 just like this up to 1 by Rn. So from here I can calculate V equivalent equal to, see, our I1 was equal to V1 by R1, I2 was equal to V2 by R2 plus Vn divided by Rn, and I will divide this with 1 by R1 plus 1 by R2 plus 1 by Rn, and this was the first equation of our Millman theorem. Okay, and I have deduced this. Now let me talk about parallel current sources. If n current sources I1, I2, In having parallel resistance R1, R2, Rn respectively, if they are connected in parallel, then these current source can be replaced by a current source I equivalent and a parallel resistance R equivalent. Let's say I have a current source I1 in parallel with a parallel resistance R1, a current source I2 with a parallel resistance R2, a current source in downward direction with a parallel resistance R3, a current source In with a parallel resistance Rn. The Millman theorem states that we can replace all the current source with a single current source I equivalent and all these resistances with a single resistance R equivalent. Okay, now what will be the value of this I equivalent? I equivalent will be the current that will be flowing through this AB path. Now if I apply KCL at this node or at this junction, you will see I1 will be incoming current, I2 will be incoming current, just like this. Let's say all are incoming currents and our In will be incoming current, and our outgoing current will be I equivalent and I3. So from which I can calculate our I equivalent will be equal to I1 plus I2 but minus I3, because this is outgoing from this node, plus all the currents plus In. Now how do we calculate R equivalent in the circuit? To calculate R equivalent in the circuit, I have to measure the resistance with respect to this terminal and this terminal, R equivalent. To calculate R equivalent, I will replace the current sources with open circuit. If I replace the current sources with open circuit, therefore I can remove the current sources. See, I have removed the current sources. Therefore, you will see with respect to A and B terminal, all the resistances are connected in parallel. Therefore, I can write our R equivalent. Therefore, I can calculate our R equivalent by using the parallel resistance rule. 1 by R equivalent equal to 1 by R1 plus 1 by R2, just like this, up to 1 by Rn. Therefore, our R equivalent will be equal to 1 divided by 1 by R1 plus 1 divided by R2 plus 1 divided by Rn. Okay. Now let me talk about the third case, when the voltage sources and current sources will be in parallel. See, in this circuit I have voltage source in series with resistance R1, a current source I1 in parallel with resistance R2, a voltage source V3 in series with resistance R3. If I have a circuit like this, in this circuit I can apply Millman's theorem. That means I can convert all the sources into a single voltage source or current source, and all the resistances to a single resistance are equivalent. Let's say I am talking about the current source only. To calculate the current source, I will convert this voltage source into a current source and this voltage source into a current source, and the result is a set of parallel connected current source. Therefore, we can replace all the current source with a single current source. Or if I talk about the voltage source, the circuit contains voltage source. I will convert this I1 in parallel with resistance R2 into a voltage source with a series resistance of R2. Therefore, I can replace all the voltage sources with a single voltage source. I will show you an example use how do we analyze this kind of circuit using Millman's theorem. Okay, that's it. Thank you.